All right, so in today's lesson, we're going to be talking about the second law of motion, or Newton's second law. And as I mentioned in class, it is the most important equation that we have in all of mechanics. So you can actually see that statement right here. So to start things off, we'll kind of take advantage of the activity that we did today or yesterday or whenever you did it for your individual class. But it basically says when there are unbalanced forces, then the object must accelerate. Okay, now this is not that surprising. If you push on something, you expect it to actually gain or lose speed. But what may be surprising is that the rate that it accelerates at is directly proportional to the net force, which we'll talk much more about net force in just a little bit, and also inversely proportional to the object's inertia. Okay, and I have in parentheses here its mass. Right, so the amount of mass something has is directly related to the amount of inertia it has. All right, so it can be summarized into the most important equation in all of mechanics, which is the acceleration is equal to the F net over the mass. And I like this way, although it ends up being a little bit easier to solve problems. Often when we solve problems, we write it as, and in most textbooks you'll find it as F net equals ma. But this kind of gives you a real indication of cause and effect. So the effect is the acceleration, and the cause is an F net, or I guess you could, by altering the m, you can have a slightly different acceleration for the same F net. Right? So the causes are on this side, the effect is on that side. And it's important to note that this equation only holds for a constant F net. Okay, meaning that we're not going to be changing the F net and looking at this acceleration. We'd have to involve calculus in order to handle that. So the units of the force are the units of mass times the units of acceleration. So mass, as you can see from the lab, that are measured in kilograms, and then accelerations, as you know for quite some time now, are in units of meters per second squared. And so the units for force are kilogram meter over second squared. Now this is a bit to say every time, so in many cases where we have a unit that comes up again and again and again, we use it as a derived unit. So this unit is actually named after Isaac Newton himself, and this is called a Newton, which is in, we use the symbol capital N in order to denote a Newton. So let's take a couple examples, look at a couple examples when we have a net force. And yeah, so we'll definitely talk about much more complicated examples as time goes on here. So we have a net force of 20 newtons. We have a net force of 20 newtons that's acting west on a 4 kilogram block moving 3 meters per second. This is 3 meters over seconds east. So if we start listing what we have a net force of 20 newtons. We have a mass of 4 kilograms, and then the initial speed or initial velocity is 3 meters per second east. So this is going east, this is going west. Okay, so we'll come back to that in just a moment. But first thing I want to do is find out the acceleration. So A is equal to F net over m. And we have 20 newtons west, so 20 newtons. So I'm going to call the west direction negative. Okay, so 20 newtons west negative. And then divided by 4 kilograms. And so I get a negative 5 meters per second squared. All right, so the question is actually what must happen to the block. So the reason I included the negative, notice that the force and the velocity are in opposite directions. All right, both of them being vectors, they have directional aspect to them. When something's moving east but then pushed west, it is going to slow down. All right, one of the things we talked about when we discussed kinematics is when the acceleration and the velocity are in the opposite direction, positive, negative, then the object will slow down. So the follow-up question to that would be, what happens when there are no more forces acting on the block? What will happen to it? Well, in order to answer this, we have to think about what do objects do when there are no more forces or the equivalent of no more forces. The answer is it will continue to do whatever it was doing. Okay, so another way of writing that is that it will not change. Right? So the key piece of the first law is that objects that have the equivalent of a balanced force acting on it, so that is, equal forces in opposite directions, they will not change whatever they were doing. So if they were at rest, they'll continue to stay at rest. If they were moving, they'll continue to move at a particular speed in the same direction. So the next part is asking for how fast is it going after 4 seconds. So we're looking for a final velocity. So this is a kinematics problem. So that's the cool thing about second law, is that we can relate it back to our one-dimensional kinematics. So we have an acceleration of -5. We have an initial velocity of +3. And then the time is 4 seconds. So if you look at your reference tables, VI, VF, A, and T, you'll see equation 3, VF equals VI plus AT. And so this is +3 plus a -5 times 4. So +3 minus 20, we get -17 meters per second. And so you ask yourself, well, what direction is it moving? Well, it was originally moving east, which we denoted with a positive, so now that it's negative, it is moving in the western direction. Meaning that this block, not only did it slow down and stop, but it actually starts speeding up in the opposite direction. Next part is looking at if we double the F net, which of the following would double as well. So if we look at the equation, the second law, solve for F net, we have F net equals ma. And what we are doing is we are doubling the F net. Now, if we're acting on the same block, the mass of the block is not going to change, or object doesn't have to be a block. And if we double the F net, then we also double the acceleration. So B is certainly the case. Now, as I just said, that the inertia or mass of the object is not going to change. And so what else might change? Well, in order to answer that, we look at the equation that we just used a moment ago, that it's the initial velocity plus AT. And since I am doubling the acceleration, and the initial speed is typically set, I'm going to double the final speed too. So if my object accelerates at twice the rate, then I expect the final speed at the end to be twice the rate as well. So both the final speed and the acceleration would also double. So now let's say we add mass to a block. We double the amount of mass a block has. What would we expect to change? Now once again, we're using the second law, this time solve for the acceleration. And in this case, we are putting a 2 in front of the m. Now, we have to think about this from a kind of experiment standpoint. If we double the mass, okay, what's going to happen? For a constant net force, that's dividing this side of the equation by 2. Notice that the 2 is in the denominator. So whatever you do to one side of the equation, you have to do to the other. So that means the acceleration would be cut in half. Okay, so the acceleration is divided by 2. And as we see right here, that A and VF have a direct relationship. So if the A goes down by 2, then the final speed would also go down by a factor of 2. And we're assuming that nothing changed with the net force. Okay, likewise, we're assuming that nothing changed with the mass. All right, so the next part, we get a kind of a better look at how we go about solving these. Okay, so this first example, we have a 2 kilogram mass. It has a 10 Newton force that's going up. So we want to use the direction that up and right are positive and down and left are negative. Okay, and that's just based off of your XY coordinate system that you guys have been using in your math class for some time now. So plus, plus, negative, negative. So this has a net force of plus 10. There's only one force, so that is the net. Now the acceleration, which is the F net over m, okay, that's an F net over m. So that is plus 10 divided by 2, or 5 meters per second squared. And that's positive, right? This has a positive, this doesn't have a sign. Okay, so that means that the object is accelerating up. Okay, I'm going to actually cross moving out and make sure that we're talking about accelerating. Now, if we assume that it was not moving in the first place, then it would be moving and accelerating up. But if it's moving down, we don't know about the initial conditions. So the next part we're going to add in this 6 newtons down. So now what I need to do is I'm going to say that this is positive 10 and this is negative 6, and I'm going to add them up. So now my F net is plus 4. Okay, so now my acceleration is plus 4 over 2, or plus 2 meters per second squared. Now the next question is, suppose I have an additional 4 newtons down. So if we think about what's going on here, now I have a total of 10 down and 10 up. So first of all, what I could say is my F net would be equal to 0. Okay, and if my F net is equal to 0, then my acceleration is equal to 0. And so one way of thinking about it is that this object would continue doing whatever it was doing, or not change, or stay the same. So what do we do if there are 3 forces? Well, we do the same thing that we did just a moment ago. We make the ones that are going to the up or to the right positive. So we have positive 4, positive 3. And this one is going to the left, so that's negative. Okay, notice that it doesn't matter where the arrows are pointing. If they point to the right, positive. If they point to the left, negative. So I have a total of 7 to the right, 9 to the left. So I say that my net force is minus 2 if I add up all those values. So then my acceleration is minus 2 newtons over 4 kilograms, or 0.5 meters per second squared. And actually I should add the negative in there. Okay. If the mass of the object was cut in half, by how much would the acceleration change? Well, this is a proportion problem. Right? So if I cut the mass in half, okay, that's the mass is going down by a factor of 2. And one of the important things that we saw from the lab is that acceleration and mass have an inverse relationship. And so if the mass goes down by a factor of 2, the acceleration must go up by a factor of 2. Okay? So this is going down, this has to go up by the same factor. So the acceleration would be twice as much. So if the original acceleration was 0.5, negative 0.5, then the new acceleration would be twice that, or negative 0.1. Sorry, negative 1. So this next example, we have a slightly different situation. What we know is that the F net is minus 21, and we know that there's some unknown force going down and then some known force also going down. But what we know is that they add up to 21. Okay? So if we think about this, what we're saying is that, x minus 6 is equal to minus 21. Okay? So how much does F have to be in order to add up to negative 21? So that is that it must be 15. And more explicitly, it must be 15 down. But since we're just looking for the magnitude or the absolute value of that force, we can just write it as 15. And the acceleration would be the net force, which is minus 21. That's the given. Divided by the mass of 3 kilograms. And 21 over 3 is equal to 7. But it's a negative 7 meters per second squared. What's the direction of, if the acceleration is 0, what must be the direction of F? Well, if the 6 is going down, we want to make an A of 0, then the direction of F must be up, and its net force then would have to be also 0. The amount of F would have to be 6, and it'd be 6 newtons up. So on the next page, we're going to skip number 4 and we'll finish that in class. On the next page, try number 5 and 6 and we'll compare answers when you come to class tomorrow. All right. Thanks for watching. Have a good night. Bye-bye.